Welcome to Stewart Science. Today is the last episode in our series on moving objects. So we've been going through talking about how we represent objects that do not have a constant speed, objects that are speeding up or slowing down. So we've done the drawings, we've done the words, we've done the position versus time graphs, we've done the velocity versus time graphs, which is on the screen right now. And so today, what we're going to be doing is talking about calculations. If we calculate with these things, how do we do that? So I apologize for my bad handwriting. I've decided that rather than type everything out ahead of time, I'm going to have to start writing things. So I got myself a fancy little Apple Pencil. So let's get into it. I want to recap what we talked about before. With these graphs, any area in the upper half of the graph is away from the observer. Since this is the positive zone, it's going away from the observer. Anything down here below the zero on the graph is in the negative zone of the graph. So it's going toward the observer, and this zero in the middle here stands for not moving. That's confusing to us because our other graphs, the zero is the observer. But in this case, there is no observer on the graph because what this graph is showing us is how fast the car is moving. So let's look at a few examples. What this graph shows us, since it's in the positive half of the graph, is that it's going away from the observer. And since it's getting further and further from this zero here, that means it's gaining speed. So this graph starts at 0 meters per second, which means stopped, and then it gains speed away from the observer. Now, what's really interesting about this is that the slope of these lines is a representation of how fast the object is gaining or losing speed. I'll say that again. The slope stands for how quickly the object is speeding up or slowing down, which in physics, we call that acceleration. So the slope of these lines stands for acceleration. So if we looked at this graph, I count 2, 4, 6, 8, 10 for our rise. And that's positive 10. And the run is 1, 2, 3, 4, 5. So over the run would be 5. So this is 10 meters per second over 5 seconds. 10 divided by 5 is 2 meters per second is our unit. So what this means is that our car gains 2 meters per second every second. Another way to write this would be 2 meters per second squared. Same thing. Let's look at another example. This one starts really high and then goes low. So it's a little bit harder, but we can still find its rise and its run. It starts at 1, 2, 3, 4, 5, 6, 7, 8, 9. So it goes from 9 to, this is -1, -2, -3. So going from 9 to -3. To find the change, if you remember, we take the end minus the start. So this would be -3 minus 9. So our change in velocity would be -12 meters per second. That's our change in velocity. Now, that happened in a certain amount of time. It happened in 1, 2, 3, 4 seconds. So this would be our -12 was our rise. It fell 12 divided by our run of 4 seconds. So -12 divided by 4 is -3 meters per second every second. Another way to write that would be -3 meters per second squared. It's negative because our line goes down. Let's look at another one. This one starts from 0 and goes up to 5 at 10 seconds. So our rise is 5. 5 minus 0 is 5. It's gained 5. So the rise is 5 over the run of 10 seconds. So 5 meters per second, that's our rise, over 10. That's bad handwriting. Let me try that again. 10 seconds. This is going to be 0.5 meters per second. Every second, the car's speed increased by 0.5, or 1/2 meter per second. Do another example here. I didn't even count this one ahead of time. I just randomly drew this. So let's take a look here and see what we got. We start at 1, 2, 3, 4, 5, 6, 7, 8 meters per second. We end at -1, -2, -3, -4, -5. So we end at -5 meters per second. So to find our change, we take our end minus start, -5 minus 8. And that's going to give us -13 meters per second. That's our change. Our speed went from a +8 to a -5. So it went down 13 meters per second. The time that it took, the run on this, is 1, 2, 3, 4, 5, 6, 7. So our run would be 7. I have to get my calculator out, but let me do that. 1.86 meters per second squared. That's my acceleration. Oh, but I screwed something up. It's negative 13 meters over 7 seconds. This would be negative 1.86 meters per second squared. So to give you an abstract, to take all of this and turn it into an equation, the rise over run is the slope. In our case, our rise was how much the velocity was changing by. So the rise would be change in velocity. Our run on that axis was time. If you look back at these graphs, we have velocity over here, we have time here. And then we said the slope of this, the change in velocity divided by time, equals acceleration. This is our equation. Delta V over t, which is velocity divided by time, equals acceleration. If I wanted to, I could write this in a more algebra-friendly way. If I wanted to get no fractions so that would make our calculations easier down the road, I would just need to move the t off the bottom of the fraction. And to do that, I just multiply both sides by t. So I'd be left with delta V equals A times t. That's just another way to write the same equation. So let's do some practice problems with those equations. So you see our equations on the left. We have 20 meters per second per second. This unit tells us that it's an acceleration that we're measuring. And this unit tells us that it's a time. So I'll take this 20, I'll put it in for acceleration. I'll take this 4, and I'll put it in for time. And so what I'll end up with is 20 times 4 equals change in velocity. If I do that math, I get 80 unit meters per second. Easy peasy. Let's do another one. This time, I have a second, which goes in for t, and a change in velocity at -18 meters per second. That tells us it's a velocity. So that goes here. This is a little bit harder, but still very easy. If I'm looking for acceleration, I just plug these two numbers where they go. So I'd have A, I don't have that, I'm looking for it, times 3 equals -18. It's just an easy algebra problem at this point. divide both sides by 3. You're going to be left with A equals negative 6 meters per second per second. Ta-da! Now this one's a little bit trickier because this time I'm looking for time. I have an acceleration. I have a change in velocity. And so I need to use my equations. If I tried to use this one right here, our time would be on the bottom of the fraction. That would get pretty messy. So this one right here will never let you down. That will never be hard to calculate. So I have an acceleration. I put this number right there. I have a change in velocity. Put that number right there. And so all I have to do at this point is negative 2.5 times t equals negative 15. To get the t by itself, divide both sides by negative 2.5, divided by negative 2.5. I get 6. And that's a time, seconds. Ta-da! Another one. The only thing I can do to make this a little bit more difficult is give you two velocities. Now you might be confused. Where does this go? I need to figure out my change from those two numbers first. Remember, we do end minus start. So 25 minus 13. I'm going from 13 to 25. So 25 is my end, 13 is my start, and I'd be left with 12 meters per second. Now that number gets used here for my change with velocity. That's an acceleration because meters per second per second. So now if I plug all my numbers where they go, I just had to do an extra step to get my change in velocity. So now I just plug these numbers where they go. 3 times t equals 12. Very easy math. Divide both sides by 3. Divided by 3. T equals 4. And since it's a time that I'm finding, seconds. Got one more example. This time I have a negative velocity and a positive one, but I'm still going from negative 14 to 10. So again, I do my end minus start. 10 is my end, minus 14, which is my start. Sorry, minus negative 14. That's why this one's tricky. Our starting is negative, our ending is positive. So you just need to plug our numbers where they go. Be confident. End minus start. 10 minus negative 14 equals 24. That's our delta V. So we plug that in right there. I still have my accelerations 3 meters per second per second. So if I do some math here, 3t equals 24. Very simple math again. Divide both sides by 3. T equals 8 seconds. That's all there is to it. As always, this is Mr. Stewart. Keep learning, no matter what.